Hello everyone, how are you? First of all, warm greetings on New Year 2021. It's a cold day today, but the greetings are very warm. So two things are very important in this new year. We are going to discuss motion under central force. And another thing is integral equation of orbit. So this is a very interesting topic. First, let us see what is the central force motion. We have taken two examples. One is familiar solar system. Another example is of atom. So these two examples are of central force motion. Here, the force is towards the center along the radius vector. So here again, the example of Earth is taken and satellite is moving around in a specific orbit. Now, force is always towards the radius, towards the center of the earth. So this is the one more example of center force. Now, there are two types of inverse square law of forces which are responsible for center or central force motion. Now, one is attractive gravitational force, another is attractive Coulomb force. So that is for unlike charges. So our atom is the example of the Coulomb force. And second example is repulsive Coulomb force, and that is for the like charges. Now let us come to the definition and some part regarding the central force motion. Now we consider here the conservative central forces where potential is a function of r, or that is the radius, and that is acting along, force is acting along r. So as we have seen in the previous case, the potential is depending on radius vector r, and force is applicable towards or along the r. Now we consider here a single particle of mass m moving about a fixed center of force and taking its origin of the coordinate system. So again, we go back to our previous slide. We consider this is the origin of the coordinate system. And one particle is moving around a center of force. Here, the potential energy is dependent on the radial distance. The problem has a spherical symmetry, and therefore, any rotation about any fixed axis can have no effect on the solution. So this is actually a spherical symmetry, and we have shown over here a spherical symmetry. So any solution about the fixed axis have no effect on the particular final solution. So hence, angle coordinate representing the rotation about the fixed axis is cyclic. It's not present. So angle coordinate is not present there. It is having no effect on the solution. If the system is spherically symmetric, then total angular momentum vector L is represented as L vector L equal to R cross P. And like that, mod R, mod P sine theta. And here R is always perpendicular to L because it is a cross product. So these three are mutually perpendicular to each other. And if R and P are in the same direction, if sine theta is equal to 0 or theta is equal to 0, then the angular momentum L is 0 because sine theta is equal to 0, the cross product is 0, so angular momentum value L is equal to 0. And in that case, R and P both are in the same direction, and that shows a linear motion. So in case of linear motion, angular momentum is 0 because sine theta is 0, and ultimately the angular momentum becomes 0. Now this motion is described by spherical polar coordinates because it is having a spherical symmetry. And because of spherical symmetry, it is convenient to use spherical polar coordinates. It is r, theta, phi. And due to its spherical symmetry, here theta is azimuthal angle. So here the theta is shown. It is described in spherical polar coordinate system. Phi is zenith. This is the zenith. and r is the radial distance. So r radial distance is shown. So r theta phi coordinate system is in the diagram, it is described like this. Now, by selecting a polar axis in the direction of angular momentum L, the motion is always perpendicular to the polar axis, and phi has only constant value of pi by 2 and can be dropped in further equations. Now, if you take the polar axis in direction of L, polar axis in direction of L, or L in the direction of polar axis. So this angle becomes pi by 2. This angle becomes pi by 2. And this angle becomes pi by 2. This phi angle becomes pi by 2. So it is having a constant value. And that constant value appears in subsequent equations. So that constant value can be neglected because every equation is having a constant factor of pi by 2. So that can be neglected. So hence, in the further discussion, we'll omit phi, only r and theta will consider, not phi. The reason is given over here. Again, it is shown in the diagram. If you take angular momentum in the direction of polar axis, then phi becomes pi by 2, and ultimately that constant factor can be dropped for a convenience in the subsequent equations. Now, Lagrangian in polar coordinate system can be written as L Lagrangian kinetic energy T minus V. We know this definition very well. So Lagrangian in polar coordinates, because we have taken phi as a constant value and that is dropped. So only theta and r are there in Lagrangian. So Lagrangian in polar coordinates can be written like this. This represents the kinetic energy term. This represents the polar potential energy term. So we name it as equation number 2. Now, as mentioned earlier, the theta is cyclic coordinate and not present in Lagrangian. And therefore, Lagrange equation can be written like this. D by d theta, del L by del theta dot, del L by del theta is equal to 0. That is standard Lagrange equation. Now, we have mentioned in our first slide that theta is cyclic and not present. And that is why the second term is dropped. It is not present. Cyclic means not present. So therefore, d by dt, del L by del theta dot, and that is equal to p theta. Now, if you represent this is equal to p theta, this is represented as p theta, then it can be represented in a subsequent slide. So using equation 2 in equation number 4, let us go back, equation number 2 in equation number 4. And this shows that p theta. Now p theta means d by dt of p theta means p dot theta, and that is equal to 0 means p theta is constant, because any differentiation of constant quantity is 0. So that is equation number 4. Now using Lagrange equation 2 in equation number 4, it is del L by del theta dot, that is represented as p theta, and that is again putting the Lagrangian function. So equation number 2 we are putting, this equation number 2 we are putting in equation number 4. So del by del theta dot 1/2 m r dot square plus r square theta dot square, that is a kinetic energy term, minus Vr, that is a potential energy term. And we know that it is only differentiated with respect to theta dot. This term will be constant, this term will be constant, because there is no function like theta dot, there is no function like theta dot. So this differentiation will be 0, this differentiation will be 0. So only theta by theta dot and del by del theta dot is 1/2 mr square theta dot square. So only this will be there to be differentiated. And if you differentiate, it will become 1/2 mr square theta dot. Now using equation number 5, p dot theta is equal to 0. So that is again p dot theta is equal to d by dt mr square theta dot, again mr square theta dot. Now this can be mr square theta dot after putting the value. So this is nothing but equal to constant quantity L, because this is equal to 0, differentiation is equal to 0, means P theta is a constant quantity. And this P theta constant quantity is mr square theta dot is equal to small l. So this is the constant magnitude of angular momentum. So this is represented as small l. This is a constant quantity. This is equation number 6. We'll be using equation 6 frequently in this discussion as well as in the discussion in future. So writing Lagrangian in coordinate r. So earlier we have written Lagrangian equation for coordinate theta. Now we are writing the Lagrangian equation for coordinate r. So d by dt del r del l by del r dot del l by del r equal to 0. We name it as equation number 7. Now using equation 2 in 7. So again, same equation, equation number 2, we are using in equation number 7. So d by dt 1/2 mr 2 mr dot minus 1/2 2 mr theta dot square plus del v by del r. And now this is nothing but mr 2 will cancel out. So d by dt mr dot minus mr theta dot square plus del v by del r. Now we do very simple thing over here. Then it is mr double dot. So d by dt of mr dot is mr double dot. The second term is as it is mr theta dot square. Then this term is taken over the right hand side. So if it is taken, if we take on the right hand side, it becomes minus del v by del r. And we know that the definition of force, it is a negative potential gradient. So negative potential gradient is represented del v by del r is equal to fr. Now using, we call it as equation number 10. Sorry, equation number 8. So we call it as equation number 8. Now the second term, we are multiplying and divide by mr cube. We multiply and divide by mr cube. This term is multiplied and divided by mr cube. And then again using equation number 6. Here, this equation number 6 we have used. So it is mr double dot l square minus m minus divided by mr cube is equal to fr. So here you can see that mr cube multiplied and divided. And then we have used equation number 6. And that by using equation number 6, we have modified the second term and we call it as equation number 9. Now, on the basis of general energy conservation theorem, one can write the total energy is equal to kinetic energy plus potential energy. So total energy is equal to 1/2 mr 1/2 m in bracket r dot square plus r square theta dot square plus vr, and that is equation number 10. This is the kinetic energy term. This is the potential energy term. So this is giving a total energy. Now, again going back to our previous equation, that is mr double dot minus l square divided by mr cube is equal to f of r. That equation we have derived in our previous slide. Now we just modify this mr double dot, taking this to on right hand side. So L square divided by mr cube plus f of r. Then we take this L square divided by mr cube minus, we write in terms of a potential energy. So negative gradient of potential. So del Vr by del R. Now if you want to take del R common, then we have to differentiate. So we have taken differentiation out. So we have to integrate it. So once we open the bracket, we get the original term. So we have taken this differential out of the bracket. So minus del by del R, Vr, this is the term. This we have taken after the integration. So if we integrate, if we open the bracket, we'll come to this part automatically. So this is equation number 10. Now multiplying both the sides by r dot. So this side is also multiplied by r dot. So mr double dot r dot again minus del by del r. this whole equation multiplied by r dot. Again, the same thing we have done it because we have taken d by dt out of the bracket. So we have to do same trick whatever we have done it over here, integration. And if you open it up, we'll come to this particular part. So d by dt 1/2 mr dot square and minus del by del r br plus 1/2 L square divided by mr square dr by dt. So this is equation number 12. Now, assuming that the right hand side of equation 10 can be written as function of gr. So now we are considering some function gr. This right hand side of this equation, the bracket. So gr is equal to vr plus 1/2 L square divided by mr square. And this is equal to the kinetic energy term. Now the total time derivative of gr can be written as dgr by dr and dr by dt, d by dt gr. So total time derivative can be written in calculus very easily like this. Now converting on this side, equation number 10 is equivalent to d by dt 1/2 mr dot square, that is the kinetic energy term, minus d by dt vr 1/2 L square divided by mr square. Now d by dt, we are taking this term on this side, left hand side, and equate it to 0. So d by dt of this term, d by dt of this term, and that is equal to 0. So again d by dt of this term, d by dt of this term is equal to 0. So differentiation becomes 0. The quantity is constant. So that is why this quantity 1/2 mr dot square plus 1/2 L square divided by mr square plus vr is equal to constant quantity, and that is equal to total energy E. So that is equation number 13. Now we focus on equation number 13. This is equation number 13. We are rewriting this equation over here. So it is 1/2 mr dot square plus 1/2 L square divided by mr square plus vr is equal to E. Just repeating our equation number 13. Now focusing on this, 1/2 mr dot square is equal to, take all this term on the right hand side. So E minus VR minus 1/2 L square divided by mr square. Now writing it for r dot square. So naturally these 2m will go on the right hand side. So 2 divided by m. E minus VR 1/2 L square divided by mr square. Now writing it for r dot. R dot is nothing but dr by dt. Again equal to, in bracket, 2 divided by m. E minus VR minus 1/2 L square divided by mr square, and we have taken a square root, so it is raised to 1/2. Then we rewrite for dt. So we write for dt. So naturally if we write for dt, the other terms will go into denominator. So dr in the denominator, the whole term. So in bracket 2 divided by m, E minus VR 1/2 L square divided by mr square raised to 1/2. Now this is a differential term. So if you want to integrate, then this becomes integral. So this term is also integrated. This term is also integrated. Now this is known as a time integral. That shows the dependency of T and R in terms of the constant E, L, M. So in terms of constant E, mass, and L. So this shows the dependency on time with R in terms of constant, that is the total energy, M is the mass, and angular momentum is also constant quantity, L. So these functions represents the variation or dependence of time with respect to R in terms of the constant of integrals, that is E, L, and M. Now that equation is known as a time integral, but this time integral can be converted into integration equation of orbit. So right now we name it as a time integral. This integral equation of orbit is in form of a t as a function of r in terms of the constant of integration like E, L, and etc. So this time integral can be converted into integration of different integral equation of orbit. Now we come to the last but one slide. These are known as a Kepler's problem. And we are familiar that Kepler's equations can be derived by these equations of orbit very easily. So time integral is a basic equation. From that, we can derive integral equation of orbit very easily. Now, this is a picture of Johannes Kepler. In German language, J is pronounced as Y. So Johannes Kepler, a German astronomer, mathematician, and astrologer. And I also request you for further reading, you can refer Classical Mechanics by Goldstein. It is mentioned over here that for further reading, you can refer Classical Mechanics by Goldstein. And the last slide, the thank you very much as I was preparing for some meeting. And these are the stars, flowers looking like a star on the ground. And you must have seen this type of flowers in surrounding. These are grown in my garden. In early morning, these flowers drop on the ground and they look like stars fallen on the ground. So these are the stars on the ground, and I was preparing some meeting. Thank you very much for patient hearing. Thank you very much. Thank you.